Thank you very much, and good afternoon, everyone. I hope you've been enjoying the first day of the conference. My name is Krystin Kadonsky. I'm a PhD student. Oh, microphone?
Maybe it's just me.
Hello, testing. Do you want me to get closer to it? Okay, sorry. I'm very quiet.
I think once folks settle down in the coffee break too.
Okay. But I'm a PhD student working with Dr. Mark Edwards and Amy Pruden at Virginia Tech. And today I'll be presenting to you our project on how waste disinfectant alters the optimum temperature for Legionella pneumophila proliferation in water heaters. Okay, so electric water heaters within premise cooling systems, microbially and chemically complex environments, and over time sediment can accumulate at the bottom of them. And we are particularly interested in this bottom layer because the sediment is nutrient rich and poses as an environment to support a variety of microbial growth, while potentially protecting pathogens from disinfected. In addition, the temperature within the sediment can vary from 10 to 66 degrees Celsius due to several different variables. And with this, we observed that temperature in a master variable that affects microbial growth rates and disinfectant decay, which leads to the question of how does temperature affect microbial ecology and Legionella pneumophila growth in systems treated with chlorine and chloramine? But before we can address this question, let's look back at conventional knowledge of how temperature relation to disinfectant decay, which is that both chlorine and chloramine decays faster at higher temperatures. But our novel hypothesis is that it is an oversimplification, and with the presence of nitrifying bacteria, chloramine may decay faster at around the optimal growth temperature of nitrifiers through the process of nitrification, as opposed to temperatures where it is assumed to decay the fastest. Now, how does this hypothesis impact Legionella growth in a worst-case scenario where disinfectant has completely decayed? In a previous chlorinated system, the expected growth curve of Legionella may look something like this, with the highest risk growth potential between 38 and 47 degrees Celsius. And in a previously chlorinated water, chloramine would also have auto-decomposed into free ammonia, which is a food source for nitrifiers. While it is not known how nitrification affects Legionella growth, the process of nitrification can increase the total organic carbon of water, which may increase levels of Legionella. But at the same time, this process has the ability to lower pH and dissolved oxygen, which may inhibit Legionella growth. And so now what if the distribution system has an intermediate level of disinfectant present? We would expect chlorinated water to show a high decrease in Legionella concentrations, but we suspect the optimal growth temperature potential to shift to a higher temperature due to chlorine decaying faster at higher temperatures. And in chloramine-treated water, we suspect that there's also a decrease in Legionella growth, but due to nitrification, the optimal growth temperature of Legionella may shift to a lower temperature, closer to optimal growth temperature of nitrifiers, where we hypothesized earlier chloramine may decay faster. And so to observe these shifts in optimal growth temperatures, we created simulated glass jar water heaters, initially filled with sediment from a full-scale electric water heater that never received much disinfectant and was inoculated with environmental strain of Legionella pneumophila. And then we split these jars into 6 different temperature conditions, ranging from 20 to 48 degrees Celsius. And each temperature was separated into 2 different categories, chlorine dosed and chloramine dosed, ran in triplicate, and for a total of 36 jars. And Legionella pneumophila levels were analyzed using Legialert, while a flow cytometer was used to determine the intact cell counts, which were related to total biomass in the jars. And for all chlorine testing, or all chemical testing, we used hot colorimetric tests. And so there are 4 phases I'm presenting to you today of this project. In phase 1, all the jars were acclimated to 37 degrees Celsius and confirmed to be replicate reactors using Legialert and total cell counts. And following this, the jars predestined to receive monochloramine were dosed with 1 milligram per liter of ammonia 3 times a week to simulate the loss of chloramine disinfectant residual, while the jars predestined to receive chlorine received no additional dosing to represent the loss of chlorine disinfectant residual and to act as our control. And this phase lasted for 12 weeks. So to observe ammonia decay in the jars, we observed the rate at which ammonia disappeared hourly on 4 separate occasions throughout the 12-week phase. We found the fastest rates of decay were shown at 37 and 43 degrees Celsius, which is different from the expected 25 to 30 degrees Celsius optimal growth temperature range for nitrifiers. And in addition, we quickly observed 48 degrees Celsius ammonia stopped decaying entirely in this phase. And so from these rates, we wanted to observe at what temperature the greatest concentration of biomass occurred. And this graph shows that control reactors that did not receive additional dosing after 12 weeks. And interestingly, cell counts decreased across temperatures until 48C, where we saw a drastic increase in intact cell counts. And now comparing this to our ammonia jars, we saw a similar trend in total biomass, where 48C also showed this drastic increase, attenuating the diverse microbial community propagated by sediment accumulation over premise plumbing. And overall, we observed that nitrification showed little effect on total biomass. And so now, what about Legionella pneumophila? Well, our control for the experiment was different from the expected optimal growth range for Legionella, which was 38 to 47 degrees Celsius. And so what we saw, the highest levels of Legionella pneumophila were 20, 37, and 43 degrees Celsius, while 48 degrees Celsius showed no Legionella positivity. And in the jars with ammonia and experiencing nitrification, Legionella pneumophila levels of the reactors were similar to those without ammonia addition after 12 weeks, indicating nitrification had little effects on Legionella pneumophila. Now, moving into phase 2, we introduced trace amounts of disinfectant into the jars. And the jars receiving 1 milligram per liter 3 times per week of ammonia previously are now in addition receiving 0.05 milligrams per liter of chlorine. And our control jars were introduced with 0.05 milligrams per liter of chlorine 3 times a week to determine how even a non-detectable amount of disinfectant can impact Legionella growth and microbial communities. And we observed this phase for 9 weeks. And so after these 9 weeks, total biomass in the chlorine jars decreased drastically. However, the chloramine jars showed a little bit of a different trend. At temperatures between 20 to 30 degrees Celsius, the total biomass levels stayed relatively stable to our control that received no disinfectant, which is interesting since, again, this temperature range reflects the total optimal growth range for nitrifiers. However, the temperatures between 37 and 48 degrees Celsius experienced a decrease in total biomass. And after the introduction of trace chlorine, Legionella pneumophila levels decreased as expected, but instead had the highest Legionella concentration at 37 degrees Celsius instead of at higher temperatures, as we hypothesized earlier. And this may be a result of our Legionella pneumophila strain being less hardy and unable to survive at 48 degrees Celsius. And after the introduction of trace chloramine, however, the Legionella pneumophila population was drastically decreased, even from a non-detectable quantity of chloramine at all temperatures. And once this decrease was observed in the total biomass and Legionella pneumophila in the jars, we stopped dosing entirely to allow for a potential regrowth period after 1 month. And after this 1 month period, we saw that neither total biomass nor Legionella pneumophila levels came close to pre-disinfection levels. And so this was indicating to us how strong of an impact even a trace amount of disinfectant can have on the microbial community. And so after this 1 month regrowth period, we replanned and moved into phase 3, where we did a 10% by volume inoculation of each reactor with inoculum from pilot scale chloramine rig that was dosed with chloramine daily, experiencing nitrification, and had Legionella pneumophila present. And then the jars receiving trace chloramine were increased to a dose of 1 milligram per liter, so we increased chloramine. And in addition to ammonia dosing, while the jars previously receiving trace chlorine received no additional dosing to act as the control, and we observed phase 3 for 6 weeks. And so after this, we moved into phase 4, where we stopped dosing disinfectant in all reactors entirely to observe another potential regrowth period. And so in this phase, we hypothesized chloramine would decay the fastest between 25 and 30 degrees Celsius. And to our surprise, we found chloramine decay the fastest at 25 and 37. And in addition, 43 and 48 stopped decay at 0.05 milligrams per liter. And this shows us that nitrification can cause chloramine to decay faster at lower temperatures compared to higher temperatures. So now, after 10 weeks of allowing the previously chloramine jars to regrow, the total biomass reached a similar equilibrium to pre-dosing conditions. And for the monochloramine jars, we dosed 1 milligram per liter 3 times per week for 6 weeks, and observed the total biomass dramatically decrease to near extinct levels. And from here, we moved into phase 4 to observe a 4-week regrowth period for total biomass. And we observed a dramatic increase in total biomass as the jars now continue to shift to an equilibrium. Now for Legionella pneumophila, after 8 weeks of no disinfectant added, the previously chlorinated jars almost came back to control levels, but not quite in all conditions. And in the monochloramine dose jars, after 6 weeks of intermediate disinfectant addition, the Legionella pneumophila levels were entirely extinct across all temperature conditions. And once this was observed, we stopped adding chloramine to the jars to establish a 4-week regrowth period and observed that Legionella pneumophila, after 2 weeks of allowing regrowth, is still nearly extinct in all conditions, potentially coming back in 25. But this is currently where our project is at, and we have so much more that we can currently ongo and observe. But let's take it back to what we learned so far. So I'll go back to our main question. And in phase 1, with no disinfectant present, nitrification had little effect on Legionella pneumophila growth and total biomass. In phase 2, trace disinfectant, it notably impacted Legionella pneumophila populations of both disinfectants. And also nitrification occurred at a maximum of 37 degrees Celsius. However, it provided little protection to Legionella pneumophila. It was still 1. And then in phase 3, when we introduced intermediate chloramine disinfectant, so contrary to conventional knowledge, the nitrification at temperatures between 20 to 37 degrees Celsius can remove chloramine disinfectant residual faster than higher temperatures. And for phase 4, our regrowth period, once disinfectant is no longer present, biomass continues to grow to an equilibrium, and also Legionella pneumophila did not grow back as expected in most temperature conditions. So I would like to acknowledge that this project was partially funded by the Institute for Critical Technology Applied Sciences at Virginia Tech. Huge thank you to all the students and my lab mates who helped with this project, and also the co-authors. So once again, I'm Krystin, and thank you for your time.
Probably time for 1 or 2 questions.
Great. Kel Traub, Johns Hopkins. Really interesting work. You know, a lot of effort goes into that. As you go forward with this, and you speculate, you know, you took a specific strain, although it was a wild type of Legionella pneumophila. Would you expect the same type of condition, say Legionella anissa or something like that? Because there's other microbes out there besides pneumophila. I was just curious if you explored that.
So not quite. Our Legionella strain is inoculated from Michigan water crisis, but then we also have Legionella from Quincy in 2 different rigs. And so I would say that they would react similarly, but most likely different, especially in these jars. So something that might come up is that we're currently doing 16S amplicon sequencing on these jars to find out what exactly is going on, because we have quite a bit of variability across temperatures and also biomass and total cell counts. And so for your question, I would say it varies. It would be variable. But yeah, I think, sorry, did I answer your question?
Sure.
Okay, thank you. Yes.
So based on these findings, are there any recommendations you would make to consumers with their water heaters, or even to like plumbing codes, or how we manage these systems?
So for homeowners and water heaters, there's kind of this trifecta of maintenance where it's between energy, maintaining no Legionella levels, and also scalding. And so for at-home water heaters, what you like to do is flush them every 6 months to make sure that sediment is removed from them. And a lot of homeowners don't necessarily do this, or they might not know about it. And so also at some point, even if you do it every year, sediment will accumulate over time. And so at some point, it's kind of a threshold of it's too late to start flushing, because it also depends on what exactly is in your water heater. There's some that are softer sediments, some that are harder sediments, such as calcium carbonate. So if it forms, it can also impact your, like in electric water heaters, there is 2 different, I should go back to this slide, but there's a heating element at the top and the bottom. That bottom heating element could be inhibited by sediment accumulation. So you might think that your water heater is working because the top element's still heating, but your bottom one's not. So you're not getting that full recirculation to kill everything within your water heater. So flushing practices, replace your anti-rod. The anti-rod is something that is going to corrode in your water heater. It's to protect your tank from corroding. So once you replace that, it'll increase the useful life for your water heater. So yeah, some things.
Sure. So how does the potential for biofilm formation in your mesocosm compare to what you might see in water filters, or in water heaters? For example, are there places that Legionella could hide out in a water heater that we're not going to see in your microcosms, or do we kind of think it's going to be the same story?
So we're hoping that the microcosms are simulating, and well, actually, that's a great question, because what we started out with, before we did that inoculation of 10% by volume, we kind of had a very thin layer of sediment. So when we saw the trace disinfectant kill everything, we were thinking, okay, maybe we need a thicker layer of sediment to allow our Legionella to hide, or even our nitrifying bacteria. So adding a thicker layer of sediment has helped us, allow for it. Basically, yeah, we're trying to simulate it the best we can. So that was kind of a lesson learned to us, is thickening the sediment to see if there's a potential for it to hide, and also get, as much as possible, a different temperature stratification in each jar. So we're aiming for 20 degrees Celsius, but we're hoping in the sediment maybe it's a little bit different.
Thanks very much. Yeah. Okay, so thank you very much. Our next presentation is by our very own Mike Fisher, who's going to tell us about the global distribution of lead and water supplies. And I think go for 15 minutes, that's fine, and we'll do questions right after that.
All right.
Okay. Let's see if we can. I actually don't know what I'm doing, I'm just pressing buttons. There we go. There we go.
All right, thanks so much for that. Can everybody hear okay if I'm like here and loud? All right, great. So this is a little unorthodox. It's a sneak preview of some ongoing work on toxic metals, a systematic review of toxic metals in drinking water in low and middle income country settings. And we thought that the lead results were relevant enough that we wanted to try and submit them for to share with y'all today. So this is preliminary results from ongoing work by a whole bunch of people, not just these folks, from a systematic review. And basically, the starting point from this, the hazard of lead and human health effects associated with lead are well known and well understood, both in terms of cardiovascular effects and other harms that we experience throughout the life course, and in particular, neurodegenerative and cognitive impairment that are particularly problematic in infancy and for developing fetuses that lead to irreversible harm, even at low levels. And WHO has produced a beautiful infographic on that. They've also produced some beautiful 2022 guidance on some of the different ways that different actors can come together to take action on lead in drinking water in global settings. And this is too tiny to read, but two of the most important takeaways from that are that the primary source of lead in drinking water globally, for the most part, is leaching from lead-containing materials in water systems. And this makes lead in drinking water almost entirely preventable. And so this kind of puts us in a unique situation where primary prevention is feasible because, for the most part, we put the lead there in the first place. And so we have sort of unique opportunities to prevent it. We've got a ton of evidence on occurrence of lead and toxic metals in drinking water in high-income country settings. But what hasn't really been done as well as we might like is synthesizing all of the available evidence about occurrence of lead and toxic metals in drinking water in low and middle income country settings. And one of the questions that we sometimes get when we start to pull this together is, well, how worried should we really be about lead in drinking water anyway? I mean, there's lots of different ways that lead exposure can happen. So lead in drinking water, is that a thing? And this is US data, not LMIC data, but this is some work that the American Academy of Pediatrics pulled together from previous studies showing that when we look at blood lead levels in children in the US over recent decades, we can actually attribute a non-trivial amount of childhood blood lead to lead in drinking water. Again, in this particular example, we're looking at ballpark 20%, more for infants who are formula fed, right? Your mileage may vary. But the big takeaway is a lot of times people ask the question, well, can we just ignore lead in drinking water? And when we look at the US example, the answer is no. If we're serious about a lead-free future, and if we're serious about addressing the harms associated with preventable lead exposure, then we can't ignore lead in drinking water in a US setting where we have lots of evidence. And so it stands to reason that if we have widespread occurrence of lead in drinking water globally, we probably can't ignore that either if we're serious about lead-free future. And so sort of our starting point here is we've got good evidence that lead is harmful, good evidence that it's important, that we can't ignore it, and good evidence that lead in drinking water is preventable. But the question is, well, how prevalent is lead in drinking water at levels of health concern globally in LMIC settings? And so one of the things that we did is a systematic review of published studies, not all the literature, right, but all the peer-reviewed literature in English, which is a limitation. But again, when we look at scientific literature in recent decades, we tend to get about 75% of it published in English, with a notable exception of evidence from China. And so not perfect, but a good starting point. We looked at studies published in the last half century from a low and middle income country context, and we looked at about a dozen metals of health concern, but today we're going to be talking about lead. Our initial search and then an update, we retrieved just an insane amount of results. We got over 25,000 results, and that was too much for a human. But we were really fortunate to be able to partner with Michelle Cawley and some others at UNC who'd done a lot of work using machine learning to train a model to prioritize a large set of results based on which ones were likely to be most relevant at the title and abstract level. And so by partnering with these awesome health science library folks, we were able to cut that down to about 7,500 and counting. And then humans got busy screening those. And as of now, we have about 2,000 included studies and counting. Thanks very much to Timothy Purvis, who's here, and many, many, many collaborators who we're going to acknowledge at the end. And so for each included piece of evidence, we extracted sort of bibliometric and geographic information, where the study was from, what water source or water supply technology it focused on, where we could disaggregate, we did. Sometimes everything's just aggregated together. Whether the site was selected on the basis of a known or suspected source of contamination. In other words, did they go looking for pollution and find it, or did they just look at water quality sort of more at a population level and characterize metal occurrence? And then we looked at the methods that were used for sample collection and analysis. Were they suitable? Where raw data were reported, we extracted and crunched those, but more often we just got summary statistics like range, mean, standard deviation, and so we made the best of what was available there. And what we have to date is a little over 800 data sets for lead, and ballpark of 48,000 observations and counting. And these were not distributed evenly, but we did get a lot evidence from a lot of different countries across a lot of different SDG regions. It's worth noting that 5 countries comprise more than half of the data. So we had a lot of evidence from India, China, Bangladesh, Turkey, and Ghana. And in Latin America and the Caribbean, we had fewer results than we would have liked. And once you move outside of Mexico and Brazil, even less evidence from that region. So we have sort of geographic evidence gaps, real dearth of nationally representative data. So the vast majority of these published results are sort of 100 samples here, 50 samples there, 1,000, but very few broad surveillance data sets of what we would have liked. So, we made do with what we had. The other thing is fewer than 10% so far are pipe sources. So again, still a lot of pipe sources, but fewer relative to what we might have liked. And so the question then was, well, can we say something useful from all of this evidence with respect to individual studies and with respect to all the data collected? And again, one of the things that we found was when you look at water quality data from a range of global settings and low and middle income country settings, we had high variability in terms of study quality. So when we looked at, hey, did you report what we'd like to know about your methods? And if you did, were those methods then suitable for quantifying lead at part per billion levels, ideally with established methods that you reported, QA/QC. Very few studies got sort of the highest possible methods quality score. Very few studies got the lowest. We had a range, but again, sort of towards the lower end of the distribution in terms of all the things we'd like to see being present and adequate. That's with respect to individual studies. Across all the studies together, we sort of said, okay, well, does the distribution of data look kind of like what we might expect it to? And based on the literature, there's a lot of evidence that toxic metals in drinking water tend to be roughly log normally distributed. And so when we plot, for example, the median concentration of lead in each reported sample set across all the sample sets and do a diagnostic plot, again, sort of across regional ranges, we do see not horrible fit to a log normal distribution, which suggests that collectively this evidence may be relatively useful, even though individual studies, there's a lot more we'd ask for in terms of reporting and methods in a perfect world. Does that make sense? And so sort of the big question is, based on what's out there, what can we learn about occurrence of lead in drinking water at levels of health concern? And kind of this high-level question, hey, is there widespread occurrence, kind of yes or no? That's really the most relevant and actionable thing. Specific point estimates, those are likely to change over time, and so we don't want to read too much into those. But when we look at just what we get from meta-regression, we see across all of our 81 sample sets, 48,000 plus observations, ballpark 30% we estimate had lead exceeding 10 parts per billion WHO guideline value. Remember, that's all the studies. When we look at the subset that were non-targeted, so they didn't go looking for a known or suspected source of pollution. They just looked at, hey, what's going on in drinking water where we sampled. Ballpark 25% we estimate exceed 10 parts per billion. And again, let's not overly focus on that point estimate, but the big takeaway is, do we see widespread evidence of lead occurrence at levels of concern in LMIC drinking water? Yeah, based on these published studies, yeah, we do. And when we look across water supply technologies, we see occurrence across different water supply technologies, so both piped and non-piped, well and other. An important thing to mention is not every study does a great job of saying exactly what types of water supply technologies were sampled, or does a great job of reporting data in a way that are amenable to disaggregation. So that makes life complex, but we're not seeing a huge story about one water supply technology being wildly different from another. We're also not seeing a huge story about LMIC, about drinking water in LMIC countries being wildly different from one setting to another. We do see a slight difference for East and Southeast Asia. However, that can be entirely explained by the data from China. So when we look ex-China, we no longer see a big difference across SDG regions so far. And we'll come back to that in a minute. We also wanted to know, hey, do we see big differences based on what type of lab instrumentation do you use? Because I'm a nerd and I like to nerd out on that stuff. And we do see a significantly lower lead occurrence in studies that use ICP-MS, but it turns out that 40% of our ICP-MS lead studies to date are from China. And when we look at this data set ex-China, that effect is no longer significant, which, just, again, we'll come back to that later, but suffice it to say, it may matter which instrument you use, but for LMICs ex-China so far, we don't see that there's this big night and day effect. That said, if you use an instrument that's not sensitive enough to quantify lead at part per billion concentrations, it's a lot more challenging to really make sort of fine-grained determinations. But with respect to instruments that are potentially suitable, maybe it matters. When we look at publication, because again, we looked over a long date range, we don't see a huge effect of when the study was conducted. Maybe some trends over time, but nothing wild going on. And again, so our big high-level takeaway, does lead occur in drinking water at levels of public health concern in LMIC water systems based on peer-reviewed evidence? Yeah, it looks like it kind of does. It looks like it occurs at levels of concern across water supply technologies, across decades, across SDG regions, maybe less in East and Southeast Asia, but that effect may be largely associated with one country. Across methods, ICP-MS may be lower, but again, we have to dig in a little bit more to why things look so different with China per se. And, right now I'll just say we don't know. It may be that lead occurrence in China is much lower. It may be that publication bias is a factor there. It may be that other things are going on with supply chains. Don't know, but it does look like it may make sense to tell the story two different ways. One for MIC settings broadly, and then separately to maybe say, hey, there may be something qualitatively different with evidence in English associated with China. Too soon to say, preliminary work. Big takeaways, though, would be available evidence indicates that there's a global challenge associated with lead in drinking water. So does lead occur in drinking water at levels of health concern? Yeah, it looks like it does. And WHO told us in 2022, it's entirely preventable. So that implies a really exciting global opportunity for primary prevention there. Importantly, there are big gaps in what evidence we have from where and the quality. And as we get more and better evidence, it's very likely that our point estimates will change. But it's very unlikely that our high-level story, that there's a preventable public health issue around lead in drinking water that can't be ignored, it's very unlikely that more evidence is going to change that story. So it looks like the evidence is sufficient to act around primary prevention. It's unlikely that more evidence is going to change the basis for taking action, even as our point estimates will almost certainly change when we get more and better data. Does that make sense? And then, like I said, point estimates are likely to change, story probably won't. So it looks like there's an opportunity for timely, calibrated communication. So it's not clear that there's a reason for people to freak out, but it is clear that we can have a thoughtful conversation about, hey, WHO gave a roadmap to taking action on this. It looks like there's a global occurrence story at levels of concern that can't be ignored, and there's an opportunity for primary prevention to improve health outcomes for kids. So let's have a thoughtful conversation about that. Yes, I think I'm over time, but suffice it to say, as we are able, we'd like to dive into gray literature, what evidence are governments and others producing. As we get monitoring and surveillance data that are increasingly nationally and regionally representative, that would be extremely helpful. And it would be amazing to find ways to turn this into a living systematic review, some sort of a platform that could be useful to folks with real jobs, right? So practitioners, decision makers, implementers, as well as, nerds like me. Thanks very much to a really long list of people on 2 continents who did the real work. And I'll stop there.
Floor is open.
So what's the timeline you anticipate for publication?
So good question. So we've already done the search update, so don't quote me on this, but I would be very happy if we have something submitted early next year, and then it depends on whichever of y'all get tapped as reviewers, if and when it comes out. But with any luck, we will have as complete a story as we're going to get, hopefully early to mid next year. And that would be entirely dependent on all of the long list of collaborators there. So, sorry, I'm trying to plug my slide deck, but I'm failing miserably. I apologize. Yeah. Do you have time for one more?
What would be the possible causes for the reduced number of publications in Latin America and in other countries? For example, that's related to it's not available in English, they're more concerned with microbial contamination and not chemical. What would be the reason for not having publications in those countries, specifically in Latin America that you said?
That's a great question. I mean, we want to dive into that. 2 things. One is, if they're available and just not in English, okay, great. We can, eventually, come up with volunteers or funding or whatever, translate them right, solvable problem. If we have fewer studies published, that's harder. It's also possible that they're published, but our search terms didn't catch them all. And so, one of the things that we'll probably do is dive into, hey, is there a big pool of evidence that we're missing in these regions, or are there evidence gaps, or is there a language barrier, or both? But to the extent that it exists and we missed it, that's sort of solvable with elbow grease. To the extent that we're missing some of the evidence that we'd like to have to answer those questions, then that sort of speaks to potentially a research agenda that's sort of, hey, how can we go get this evidence? And if governments are collecting it, but we didn't access it, can we maybe start some conversations about, are there ways to partner around crunching the data? Yeah, sorry, I'm probably over time, right?
Yeah, thank you, Mike.
Yeah, thanks so much.
Appreciate it. Really cool. Okay, I'd like to invite our third speaker, Hanen Belgasmi-Allen from CDC, who's going to tell us about pollutant surveillance and wastewater. And we had a no-show for our fourth presentation, so we are going to go about 15 minutes, about 5 minutes for you.
Good afternoon, everyone. I am, as we mentioned today, I will be talking about wastewater surveillance, monitoring of water circulation in two countries in the Americas, Haiti and Guatemala. Poliovirus belongs to the coronavirus family genus of enterovirus. It is a single-stranded positive sense-binding virus, and humans are the only natural host. There is 3 serotypes of poliovirus. There is wild types 1, 2, and 3, as well as vaccine-derived strains. Poliovirus is highly infectious. The incubation period is usually 7 to 10 days, but can range from 4 to 35 days. The virus enters the body through the mouth and multiplies in the intestines. Up to 90% of those infected experience no or mild symptoms. And the disease usually goes unrecognized. However, in the remaining proportion of cases, the virus causes paralysis. Poliovirus is shed by infected people, usually children, through feces, where it can spread quickly, especially in areas with poor sanitation and hygiene systems. Poliovirus could be detected through stool specimens, which is the acute flaccid paralysis surveillance, or AFP, and it is the gold standard for detecting cases of poliomyelitis for children under 15 of age. Or through sewage or environmental water, which is the environmental surveillance, which used to confirm the presence of the virus in absence of cases of paralysis, and it also increases sensitivity of AFP surveillance. We prevent poliovirus infection with 2 types of vaccines. The oral polio vaccine, or OPV, contains attenuated virus, used in endemic countries and to stop outbreaks. In rare cases, especially in areas with low vaccination coverage and poor sanitation, the use of oral polio vaccine may exceptionally result in the emergence of vaccine-derived polioviruses, which may cause paralysis. The second vaccine, which is the inactivated polio vaccine, or IPV, contains inactivated virus, administered through injection in combination with other vaccines, and used in industrialized polio-free countries. Wild poliovirus cases have decreased by over 99% since 1988, from an estimated 350,000 cases in more than 125 endemic countries to 40 reported cases in October 2024. Of the 3 strains of wild poliovirus, type 2 was eradicated in 2015, and type 3 was eradicated in 2019. However, wild poliovirus type 1 remains endemic in Pakistan and Afghanistan. And 5 of the 6 World Health Organization regions were certified polio-free. In 1988, the World Health Assembly adopted a resolution for the worldwide eradication of polio, marking the launch of the Global Polio Eradication Initiative. The Global Polio Laboratory Network was officially established in 1990, and their goal was to distinguish poliovirus as the cause of acute flaccid paralysis, or AFP, from AFP caused by other diseases. And environmental surveillance was added as part of the GPLN's goal for poliovirus eradication. Environmental surveillance has been used for many years to detect and monitor the reintroduction of wild poliovirus into polio-free countries and provide confidence in the successful elimination of wild poliovirus in previously endemic countries. This map shows the distribution of environmental surveillance sampling sites worldwide. And since 2016, progress has been made in expanding the global environmental surveillance network into 500 environmental surveillance sampling sites worldwide. In this map, I have it to my pointer. We have Nigeria, Pakistan, and Afghanistan are some of the countries with over 100 sampling sites. And currently there is 75 polio environmental surveillance laboratory in 51 countries worldwide. Since CDC serves as a World Health Organization as a global laboratory, we provide technical and programmatic assistance to the Global Polio Laboratory Network, or the GPLN, and part of that assistance is environmental surveillance. We are currently supporting the Pan American Health Organization, and as part of the polio elimination certification process, the Regional Certification Commission for the Polio Endgame in the Americas region assessed the risk of poliovirus circulation in the countries in case of an importation or emergence of poliovirus. For the polio risk assessment, 5 areas or components are considered, and each component has indicators with a defined score that add up to a total of 100 points. So the higher the risk, the higher the score, the higher the risk of the country. And as you could see here, why we selected Guatemala and Haiti, because the risk assessment 2014 showed that Guatemala and Haiti are considered very high-risk countries. In this slide, I will be showing how we select sampling sites. Sample collection could be done in 2 different ways, either through a wastewater treatment plant or through an open canal. A catchment area here refers to the geographical region served by a specific wastewater treatment plant or sampling site within a community. In this example, we show households equipped with closets connected to converging sewer network, allowing collection of downstream samples that represents a large population living in the catchment area referred to as catchment population. And this site will be able to monitor transit population as well. So surveillance timeline is minimum collected 1 month, and the sampling will be accounted for 1 year to make sure if the site is suitable to continue surveillance. So I'll be talking about how the polio environmental surveillance workflow starts. We start by sample collection, either through wastewater treatment plant or open canals. It could be done either with a swing sampler, as you could see here in this picture, or simply with a bucket. After sample receipt at the laboratory, we concentrate samples either with this method called the 2-phase separation method, which requires 2 days. It is the gold standard method used within the Global Polio Laboratory Network and requires the use of 2 polymers, which will allow the phase separation. The second method that was developed by CDC, which is the concentration and filtration elution method, referred to as CAFE, and this method requires only 1 day. So what is CAFE method? It is based on the very known principle of charge-based methods where electrostatic forces are instrumental in virus filter interactions. So we start with 500 ml of the sample that undergo primary and secondary filtration, utilizing 2 filters with different pore sizes. The filters then will be extracted. Then the resulted eluate will be chloroform treatment and then inoculated into cells the same day. After inoculation into cells, we follow the WHO virus isolation algorithm developed for environmental surveillance, which utilizes 2 different cell lines. And so the sample after inoculation will be observed for 5 days for cytopathic effect. Real-time PCR utilizes primers probes that are specific for enteroviruses and poliovirus serotypes and is used within the Global Polio Laboratory Network. Sequence is used for any discordant results during RT-PCR or when a problematic serotype was detected, such as poliovirus type 2. Environmental surveillance in Haiti was established in March 2016, and this map shows the sampling sites with the watershed population. We are currently monitoring 3 cities in Haiti with a total of 8 sampling sites, which are currently open canals. We collect single grab sampling, which is 1 liter collected in morning peak flow, which is around 9 a.m. And we use an Haiti swing sampler due to how the sites are. So swing sampler really allows collectors to reach underneath canals. So this will allow them, and it's more safe for them. So we collect 1 sample per month per site. And this graph, it's a little bit, don't worry about too much, it's a lot of data in there, but this shows only the results for Haiti for 2023. The blue dots refers to the non-polio enterovirus. So non-polio enterovirus is very important for poliovirus site selection. We use it as a proxy. It's a dependable proxy for polioviruses and for environmental surveillance site sensitivity. And since poliovirus is a non-polio enterovirus and have similar structure and stability and survival characteristics, so it is very important that the site has a good non-polio enterovirus detection rate. In this map, in this graph, we only detected Sabin-like poliovirus type 3 in 1 site in August 2023. Enterovirus detection as well as poliovirus detection is very low in Haiti, and this is due to the low vaccine coverage in the country. And we've been seeing this since the establishment, since 2016, so nothing has changed. It's still the same, very low vaccine coverage in the country. Guatemala environmental surveillance was established in November 2018, and we have 2 sampling cities with a total of 6 sampling sites, and all 6 sites were open canals. So it's the same thing as Haiti. We perform grab sampling, 1 liter collected in morning peak flow. However, with Guatemala, we use buckets simply because of the rocky structure of the sampling sites in Guatemala. And it's the same, 1 sample collection per month per site. So in this graph, I will be showing the results of 2019 Guatemala, simply because there was a very important result that has been detected during that year. So 3 genetically unrelated vaccine-derived polioviruses in the red dots. They were like vaccine-derived poliovirus type 1 and type 3 that were detected during that year. So the Ministry of Health of Guatemala responded by including event investigation through institutional and community prospective case searches for acute flax paralysis during 2018 to 2020, and they launched polio vaccination campaign in September 2019. As you could see here, there is a big difference between Guatemala and Haiti, and usually poliovirus detection coincide with vaccine campaigns that it's ongoing within the sampling sites. There is a lot of challenges for polio environmental surveillance. The primary challenge is the sensitivity of the test. Test has to be extremely sensitive, highly sensitive, to detect even low concentration of the virus, simply because we are towards eradication, so we can't miss any polio. It is important for representative sampling, and this is essential for an effective monitoring. Seasonal variability does affect sample poliovirus concentration, which make surveillance more complex. Other viruses and contaminants can interfere with poliovirus testing, which could result in false negative and false positives. It is very expensive. And some of the challenges we encountered in Haiti is the ongoing civil unrest in the country, which affected sample collection and sample shipment. Sampling site water stagnation, and this is due to the accumulation of trash in these open canals with time. And the low vaccine coverage, which is still ongoing, a problem within the country. And with that, thank you all.
How worried are you about missing cases because you're just taking 1 grab sample at one point in time once a month?
So usually, in other countries with outbreaks, they do it twice a month, and they have more sites to collect. Our surveillance is basically not for cases. We're not looking for cases. We're looking for if there is any person that is shedding the virus ongoing. So the good thing about environmental surveillance, if there is one person shedding within, like, let's say, like 100,000 population within that treatment plant, we'll be able to detect that there is the virus. So it could be during, before the case happens. Sometimes we will find the virus without any case. So what it does, environmental surveillance, it helps Ministry of Health, the local health, to let them know that, hey, there is someone shedding this virus. Maybe you need to increase vaccine campaigns within this area. Yes.
Given the results of your study, what's the next step for the CDC?
So this is ongoing surveillance. So we monitor on a monthly basis these countries. As of now, so what we do with Haiti is different. So usually following the GPLN rules is the site has to be, if you select the site, you see the non-polyenterovirus, it has to be within 6 months. If you open that site, it has to be 50%. And after that, you assess, either you close or you find another site that it's serving the same community. So especially if it's a high-risk community. As of now, we're continuing the surveillance and hoping that we're trying to help the country as well as understanding. But there is a lot of challenge that we can't, it's out of our hands. Specifically in Haiti, that because there is a lot of political government problems that we can't really help in that. But all we could do is continue environmental surveillance, because in the Americas, they are the only 2 countries. So we hope to have more countries do the surveillance, which will help the Americas region.
Yeah.
Yes,
Do you have any context as to the difference between the treatment plants and the open canals? You mentioned that you do some monitoring at the
Yes.
wastewater works.
For the treatment plants, it's more concise, and the virus will be, if there is any shedding within that population, it's going to be more concentrated, the virus, because it's contained, and you will be able to know what is the flow time better than we think. Everybody flushes their toilet around before 9 a.m. Everybody uses that, so we try to catch that time. Open canals could be a little bit challenging, but that's all we could have, especially in low-income countries. There is no good sewer networks. So all we do is open canals. And one of the problems we're facing with Haiti is the stagnation, a lot of trash. So certain sites we had to close because we can't collect anymore. There is no water.
Was there any influence of rainfall or anything like that on those open canals?
It does not matter. It's accumulated to the part, like even if it rains, you can't see water. There is no access to water. So open canals could be very challenging, but that's pretty much what you will have in low-income countries.
Thank you.
You're welcome. Yes.
Given the results you're seeing in Guatemala, does the CDC continue to recommend oral polio vaccine in that region?
So oral polio vaccine is currently the only thing is used in low and middle income countries, simply because it's easier. It does not require a doctor to inject. So there will be a lot of volunteers. They go from door to door and they do drops. It's cheaper. The plan is to eradicate polio, and slowly we try to move to the inactivated polio vaccine, which is the injection, which now WHO recommended for all middle and low income countries to start including IPV as a dose within the 3 doses. So 4th dose will be IPV or 3rd dose will be IPV for all children. So we're trying to add it slowly, but we're not there yet, unfortunately. Yes.
So your group, at CDC, there's a lot of interest in wastewater surveillance. So does your group work and engage with other groups at CDC who are interested in monitoring for other microbes in wastewater?
Not yet.
Not yet.
We would love to, because we try to find, develop methods that could work across the board with different pathogens, not only polio. If there will be anything, there will be a tweak, but mostly the methods we used, basically even COVID, they mimicked poliovirus. So when COVID hit and wastewater surveillance, they mimicked poliovirus, the way how it's done. So yes, everything could be done for other pathogens. following poliovirus's work that has been done already.
Yeah, there's a lot that people could learn from the experience.
Yes, 100%. Yes.
This might be a silly question, but is there any evidence on how far along the course of an open canal you can detect poliovirus? In other words, if it's shed right above your sampling site versus several kilometers away, what sort of attenuation do you see in terms of, physical processes and activation, other things, or not so much?
So when we do site visits, we usually see, okay, this is the community we're gonna collect from. And right next to it, up or at the bottom, downstream from it, there is another community. So what we see is the water flow. Where is the water coming? Is it down, especially if it's up a hill? So sometimes we take the decision of collecting from a downstream population because the upstream, eventually we will get there. But at the beginning, we do try both. And then if we see it's adding more time, more cost, then we will decide on the downstream population, because eventually, if the canal is shared between both populations, we will choose the downstream.
Okay, thanks very much. Okay, thanks to all three presenters, and I think this concludes our session, so thank you. Seemed like people would ask all the questions they wanted to ask, so.
Yeah, no, sorry, your idea of impaneling is good.
It's especially different.
I'd rather never. I'm doing not. I'm sorry, I'm not available.
Oh, that's right, I forgot you. Yeah. It's on
I have a feeling it should be different.
I didn't show that. You did not see the way of it.
Contamination. And how is that going?
We are extracting so maybe if we see different if and when, sort of traditionally represented country level data sets start to roll in, you use the same method for rural versus urban. That's where I think often start seeing a lot those supply chains are likely to be, sort of global, so it might be the same components in the rural versus urban. You can see, for example, more pipe water and surface water versus groundwater and so on.
Unfortunately, rural areas where they don't have a lot of pipe water. You should
By American Dad.
it's different surface water.
We looked at very few surface water studies. We tried to exclude those for that reason, because that was a really good point.
Life, yeah.
I love my daughter.
Oh, wonderful.
He's royal.
Daisy's got a liver ACL. She's getting $6,000 surgery.
Sometimes they heal on their own. That was my bread and butter.
It's crazy. With an pound on the wrist.
Evaluating existing and
She was my mentor.
so the short answer is yes.
No, so quick. So Daisy's gonna have her surgery.
It's something I've been working on very good. And then building up the
I did a master's in memory in Holland, and
years of college.
my entire master's thesis was about the wastewater-based surveillance, SARS-CoV-2, and that was like I published on it and everything, and so. You said that you worked with RDID.
No, we collaborate.
Okay, so
Timothy or both, sort of
and I
going
was
in the right direction. Do you have a sense of?
with like just more and Jamie Patel and Meg McCarran. Yes, wonderful team. They were wonderful. And we were interested in kind of how the presentation. Yes, I decided I took like which one. I was like, I think I'm a little bit I realized that like everybody is very good. So I was like,
And then also it's sort of like,
but
there's some things that nobody has to film because people want them and pay for them, right? And then there's other things where it's like, oh, okay, catalytic funding here, help and then sustain itself. And then there's other things where it's like, I've got a cool idea and I would love for somebody to fund it, but may or may not ever, become a free living thing in the world, right? So
It's just tasty.
two separate questions about does a new technology duplicate something that's already available, or does it provide something new and awesome? And then separately, because it can do something new and awesome, will that ever actually get in the hands of people who need it and do anything useful with it? And both of those are above my pay grade. I can help you with the first one. For the second one, use myself.
Where we're at right now.
The question about even if it is better, I'm sure anybody who gets testing for water in the real world can because the world is so full of potentials nobody has for
Choose Tiger. Optimizing my body.
Where's my jacket?
Great. Exercising some too.
You'll be able to. Yes.
or not, and might be able to find different levels. The first time I met, I would watch anything. Yes, I'll do that. So, what's I don't even know what program was, but it's not really intense exercise.
Yeah, and then maybe we can get together at a coffee break because we sort of, depending on.
I can't relate.
Trying.
And no, it may be a very
Set up my ass and drank 9 beers.
Either way, we're here for it.
Great, thank you so much.
Yeah, thanks so much. And you go by.
You coming to my party?
Yeah. Okay, great.
You are so cool.
Yeah, what's up? Okay.
But you already see people doing.
Oh, okay, Leeds. All right, yeah.
Yeah, so my background's actually data science, so Washington's very useful. But one of the things we've been finding quite interesting is most of the applications we've been using
Maybe.
the data's a lot less small for compute. But it's trying to get into emerging.
It's just with you. Cell activated.
One thing I find interesting is how you actually found using
What about
just like how your experience was with that.
It's one.
So, to what degree do you feel like there are actions? So some of the work I'm initially trying to do, it's been more difficult than anticipated, is to take systems where we can apply various machine learning
This year was having.
and then try and scale that down.
It's hard to see a brother go down like that. You know what I mean?
what you might need. Oh wow! It's a lot more difficult than initially anticipated. The idea was if you could give someone an estimate, say, because all the JP and more data, say how much we need. So we can say to people, this is exactly
I understand, but we know how.
There's some interesting ideas.
He'll bring good energy to whatever he does.
You can't really say that much about data since we don't have.
Fully committed, quite logical.
But you could say how much more crap it would be if we only had half the activation.
That's very true. It's just what you experience was because the whole it's just what were your experiences with the data you had available from your and are most of those, I think you mentioned like 47,000?
So we have 48,000 observations so far. So the machine learning bit was very unsophisticated. Well, I shouldn't say that because someone else did it and they're very smart. But what we mostly did is when you search and you get 500 results, you and some helpers read every an abstract and sort them. But when you get 30,000, then what we did is just trained a model to look at the title and abstracts and say, hey, based on this training set of 500, which ones would Mike probably want to read? And so that was all we did with the machine learning. Is we just sort of said, hey, assign a propensity score based on the title and abstract, and we'll then read the ones that seem most likely to be worth reading. And then we would check that obviously by actually doing some of them.
Yeah, like grown-up Michael Cera.
We haven't really done any machine learning or any sort of fancy stuff to try and extract the data or work with the data to answer questions. And
you could do commercials
very
for
much what we're
products.
doing, but that's one of the reasons where we'd as soon as possible, maybe try and turn this into an open data platform so smart folks like you can get in there and see if there's anything.
Psychology.
The biggest problem that we had
buy the soap. It's like
Crazy, guys. It's like $25. I don't even know why.
Yeah, exactly. Yeah.
We're not going to tell you what the results are. We're just going to tell you the range, mean, and standard deviation. And that's not very helpful because the data aren't even normally distributed. So then we made some not horrible assumptions to try and do, basically take the most plausible distribution based on the literature and fit the, and sort of fit those to the summary statistics that are provided and sort of use those as our best estimates for what the underlying data distribution probably looks like, and do that a bunch of times to get a less biased
Can he just make like a
data set versus
limited Cheetos
just pretend something's normally distributed that we know perfectly well
Be
is.
like, come to work for SpaceX.
It's such a safe assumption a lot of the time.
But I mean, the two big problems is one, it's not normally distributed, and
I'll
two,
just
everyone treats a non-detected zero, but of course,
make shitloads of money.
zero is the one number you can be pretty sure it isn't. And so, then we said, okay, let's take the method detection limit and say, okay, well, if you didn't detect it, we're going to interpolate half of your likely lower detection limit as the least biased assumption rather than treating it as zero,
Taxi,
which introduces a lot of bias. Long way to say that we started with some
It's like the worst possible thing.
variable data quality, and so our biggest problem was how to go from too many
Don't get started with that. Not right
Not
now.
to-
It's Monday, okay?
take not enough information.
Y'all can still vote here in North
try to
Carolina,
do something
right?
useful with it, but once that bit's all done, what we're really hoping is to put it on a platform and just sort of make it available to anybody who wants to play with it to come up with better answers.
That's right, yeah. And is your plan able to also include how you would
So that's been previously published, so the citation in there really talks about it, so, we'll talk about what we did this time around, but the lady who, the librarian who did that, she's actually got half a dozen papers where she's done that for others. And so, if you read any one of those, you kind of know what the deal is. So basically, she has a brilliant algorithm.
Watch till
Knuckleheads like me just tell it which of 500 papers we thought were relevant.
He was fun.
Not to train it, we just check with some
But what's
out-of-sample
interesting
stuff.
about this,
And if it's
interesting about
better
this
than
is
chance.
that
we're happy. And it turns out to be much, much better than chips. So, yeah, cheers. Vince, do you have a card or? It looks like a different person, right? Would you be interested in a heads up when it comes out to see if you can do more?
But I feel like that was like.
Again, my thought is, I mean, in an ideal world, we can all do ourselves and ask a million questions, but just it's so public health relevant, like if you just want to sprint and get it out there, and then kind of have lots
He's
of
also,
conversations.
stand up tall. He's histology. He's like your height now. So Sarah is like 1 inch taller than you, maybe.
Thanks so much.
Just taller than her. He's like,
How do you keep doing?
he's like as tall as her.
How are you?
Yeah, I gave him his first manual transmission driving lesson yesterday. So we're out on the farm.
It's very thirsty.
Like
And
driving a clutch, you know, with the truck and everything.
Yeah, please. Having the low results from the ICP.
Yeah,
14 a month.
but again, those turned out not to be significant if you take up
Having
the
the sex
data from
talk with
China.
him,
But go ahead,
entire
Tara.
podcast.
Surprised, like, because that's
great.
So you're just gonna send him the
Yeah.
What do you think the reason behind that we know already?
It probably has to do with the way we ask the question. I mean, certainly you can quantify at a lower
It's
concentration.
so great. I know, my kids.
You know, if you happen to be measuring something that is present
She's in
at high
like
concentration, you
all
know,
the
so if it's
theory
present at parts per million level, any one of those instruments, you're not going to get system.
Yeah, once you read those five.
For trillion level, well, probably none of them are going to be adequate. There's this narrow range, like, you know, sort of 0.1 to
Yeah, yes.
you know,
Sarah was like, I'll do
to
LE.
maybe 10 parts per million, where you're probably going to do much better with ICP-MS than any of those other methods. And my hunch is the way we presented the data may not be fine-grained enough to really capture the fact that it's better within that range. And what we may find
It's
is,
it's funny, like it's
one
all
possibility
at
is,
once, and he's like a different
do you
person,
get
like every
lower values with more sensitive instruments, simply because the less sensitive instruments
because
seem
he's
to
doing
systematically
bike jumps
overestimate.
like for 5 hours at a time.
You also might find that the methodological limitations of
Taking
most
electric
studies
guitar now,
are
she's
so big
shredding.
that the difference
I've
in
been
sensitivity
hearing the
between the
same
instrument
song
doesn't matter as much as the fact that you didn't acid wash your bottles or you didn't
It's in your
or you did
head,
calibration.
in your head.
When we work with labs,
Pretty good.
when they have
she's in Beauty and the
very
Beast.
high-end instrumentation,
And
they
she's
don't always
doing all
use
the
suitable
art theater things
calibrations.
at school.
And so that often
Hey.
eliminates some of the
both really
sensitivity difference between methods right there, you know?
Is Sarah
So, you know,
is she
what we
teaching
talk about
at?
is that
Okay, so she's not.
high-quality ICP-MS studies are much more sensitive than high-quality studies using other methods. But it may
And
be
everything's the same with
the
us.
proportion of high-quality ICP-MS studies is small enough that that might not be something that we're going to see in a larger data set.
Yeah, that was, I just wanted to.
Yeah.
Thank you.
Yeah.
Yeah, thank you.
Yeah, well, thanks so much.
I'll let you know tomorrow. Bye.
Good, how's it going?
We can get a beer right now. Get a beer right there.
Which university? Oh, yeah.
Let me introduce you to my colleague, Meseret.
Hi.
This is Joe
I've seen you
Brown.
before. Have I seen you before? Where
Research
where
about
are you
that
based?
as well, and what's mind reading these flicks together now.
Yeah, we work closely together, but we met for the first time yesterday, so it's super exciting.
Yeah, nice to see you. Welcome to
Actually,
the
kind of getting from collection partner.
Well, we're getting a lot of high-quality published studies from Africa. It's also quite possible that there may be high-quality studies that are not published. I think there's probably a lot of opportunity. What we didn't see really in any LMIT settings was a lot of nationally representative data. And so what we often see is like, you know, sort of 100 samples here, 50 samples there. But we didn't see a lot of high-quality nationally representative studies. I don't think they're publishing them in
Yo creo que eso ya no lo llevamos.
¿Será? ¿No se lo termina? Yo creo que ya les he hecho con ellos. creo.
No.
¿Vas a ir a la comida, verdad? No, porque viene uno a las 7. Supuestamente termina a las 7.
Finish?
No.
Finish? Could we refresh?
Okay.
We have one more program here.
Okay.
So you can start here, turning these around.
You don't have the chairs for the.
Yeah, just a little bit. That's all right, you can leave.
Did I flip these wrong?
No,
Just like this?
that's right.
Okay, so. So they're facing each other?
Yes.
Okay. I don't know why in my head I thought the chart was that they were facing out. Same number of chairs?
No, add some more. It's the same number.
Okay, it's the same.
But it's one more row.
That stays? Line up with them.
Your line's crooked. Back them up as close to the table as you can get.
Sorry.
No problem.
And do we want the gap to be like this or pull them back?
Pull them back. way?
Facing this way. Speed dating. Everybody going home safe. But this close. Where we sitting now? Look at the chair behind you. Needed that chair more.
No. We know. Oh yeah, 106. Who were there? Oh, so me too. I'm only 6.
Well, luckily we had an extra one from this row that I had.
No, this way from here and then somewhere.
Oh, good gracious. Where you taking all the chairs?
I don't know why.
It was funny. The one lady was like, sorry, we were destroying your room. And in my head, I'm like, put it back. If you know that you're doing it, then put it back. I didn't think so.
Normally they're not like this.
Well, just the higher number of people, the more likely it's had to happen.
No. I mean, we've had 600 people in here and it's like the chairs don't move. Nobody spills anything.
Should I leave these or just put them on stick?
Will you try our,
One of these more?
and this is 6, 8, 8, if look at it in diagram.
Oh,
Yeah, diagram 8, 8.
that's the wrong diagram.
Right now?
Oh.
I know, long diagram is no. Right now they make it the same, they copy paste, you know? We put here 13, right, usually, but they make only 12. They put 13 or 12. Look, they have to take only.
Well, in order to do 100, they gotta do 13. When we do.
No, because in there, usually we put only 7, and 5, and there, here is 7, so we put the other 8 here, like that. If we put 8, 6, we need only 12 here.
Yeah.
2, 4, 6, 8, okay. One more.
In the closet.
Yeah, you're right.
Well, I got 12 right here. We got 13 over there.
Is there an extra over here?
This is 13.
Only there.
There's another extra one.
Only there. Oh! 2, 4, 6, 8, 10, 12, yeah.
14, 16, 18, 20.
Is this one supposed to be here?
Yeah. But it doesn't.
It doesn't line up.
The posts are different on that one and this one.
Oh, okay.
Uh,
I was like, that one looks like an outlier.